Professor Lovász and Professor Wigderson, we first want to congratulate you for being the Abel Prize recipients for 2021. And we cite the Abel Committee for their foundational contributions to theoretical computer science and discrete mathematics, and their leading role in shaping them into central fields of modern mathematics. Our question to you is the following, and here is the background. We would like you to comment on the remarkable change that has occurred over the last few decades in the attitude of, say, mainstream mathematics towards discrete mathematics and theoretical computer science. As you are fully aware of, not that many years ago it was quite common among many first-class mathematicians to have a skeptical, if not condescending, opinion of this type of mathematics. Could you start, Professor Lovász, to comment on this?
I think that's true. It took time before two things were realized. I think actually there are two things about theoretical computer science that are very relevant for mathematics. One is simply that it's a source of exciting problems. When I finished university with some other young researchers, we started a group to study computing, computer science, and because we realized that it's such a huge unexplored field, what can be computed and how fast and how well. And then the second thing is that when answers began to come, in particular when the notion of NP, non-deterministic polynomial time, and polynomial time became kind of in the center, then we realized that the whole mathematics can be viewed in a completely different way through these notions, through effective computation and through proof of short proofs of existence, and so these two things for us young people were so inspiring that we really started to make this connection with mathematics. So I think that it took time until the rest of mathematics realized, but it gradually went. I mean, in number theory, it turned out to be very important. Then in group theory, these notions came in, and then slowly over a lot of other areas of mathematics.
Wigderson, please.
I completely agree. There is some truth in the fact that there was a condescending attitude in some mainstream mathematics, or maybe more mathematicians, towards discrete mathematics. It was probably less towards theoretical computer science, because this sort of existed in the realm of computer science and was developing, and maybe just people were less aware of it directly. I think that László is obviously right in that the very ideas of algorithms that were introduced in theoretical computer science and notions of complexity were and are fundamental to mathematics, and it took time to realize. I think that the real truth is that it was realized long ago by all mathematicians of all ages. They all used algorithms. They all needed to compute things. I mean, Gauss's famous challenge to the mathematical community to actually find fast methods to test whether a number is prime and to factor integers, is extremely eloquent, given the time it was written. It is really, calling for fast algorithms to be developed. So it's not that these were not realized. I think that more the part of discrete mathematics was viewed by some as trivial in a sense, and the sense is that if there are only finite number of possibilities that we have to test, then in principle it can be done. So what's the problem there? I think the notion of efficient algorithms, clarified what's the problem there. I mean, because, there may be an exponential number of things to try out, and you will never do it, right? So if instead you have a fast algorithm for doing it, then, it makes all the difference. And the question whether such an algorithm exists clarifies the importance of having it. Similarly, as László said, having efficient certificates, just ways of convincing somebody else that some property holds. This is at the core of making characterizations of mathematical properties. If you know that, property like that is NP-complete, we realize because of computational complexity that you are unlikely to find such characterizations. So I think this understanding evolved. It, of course, caught up first with, definitely pioneers at the time in the 70s and in the combinatorics area, in the discrete mathematical area, because that was the most natural. That's where, at least, it's easy to formulate problems so that you can attach complexity to them. And then, gradually it evolved to other parts of mathematics, and number theory is a great example because there too, there are discrete problems, and discrete methods are hiding behind lots of, famous number theoretical results. So, and then from there it gradually, dispersed on. I think by now it's pretty universal, the understanding how important discrete math and theory of computation is.
This is admittedly a naive question, but as a non-expert I have few inhibitions, so here it goes. Why is it that Turing's notion of what is called a Turing machine captures the intuitive idea of an effective procedure and, so to speak, set the standard for what can be computed? And how is this related to Hilbert's Entscheidungsproblem? Could we start with you, Wigderson, please?
Yeah, Avi will be better. That will be easier to pronounce. Yeah, of course. I think that my first recommendation would be to read Turing's paper. I mean, to read all his papers. He writes so eloquently that when you read, let's say, his problem, his paper on computing procedures and the Entscheidungsproblem, you will understand everything. There are many reasons why, or several reasons why the Turing machine is so fundamental, so basic. The first one is that it's simple. It's extremely simple. It's so simple that it was evident to Turing and to many others at the time that it's so simple it can be directly implemented, and thereby he started the computing revolution. If you look at other notions of computability that people studied, Gödel and others, and definitely Hilbert, with recursive functions and so on, they don't lend themselves to being, to make a machine out of them. So this was fundamental. The second is that it was subsequently, in very few years, proved that all the other notions of efficient, of computability were equivalent. So the Turing machine, simple as it is, could simulate all of them. So it was, encompassed all of them, but was much simpler to describe. A third one is that one way Turing motivates his model He's saying, well, look what we do, we humans do, we human calculators do when we are supposed to solve a problem. Let's say multiply two long numbers. Look at what we do on the piece of paper. Just abstract and formalize it. And when you do that, you are led automatically to my model, to my Turing machine. So that's the third. The fourth reason is the universality, the fact that with his model, he makes this point, of course, immediate, is that it's a universal model, namely that in a single machine, you can have part of the data be a program you want to run, and it will just emulate this program. So that's why we have, laptops, computers, and so on. They are just one machine. You don't have a different machine to multiply, and a different machine to integrate, and a different machine to test primality, right? You have one machine in which you write a program. That's another point. And so all these reasons, I can talk more about it, but maybe I should. That's enough. It's just an amazing sort of revolution encapsulated in a really simple notion that everybody can understand and use. So that's the power of it. Now the relation you asked about, the relation to the Untitled problem. Hilbert had a dream, and the dream had two parts, that everything that is true in mathematics is provable, and that everything provable can be automatically computed. Those were the two parts of his dream. Well, Gödel shattered the first one. He proved that there are true facts, let's say, about integers that cannot be proven. And then Turing shattered the second one. He showed that there are, provable things that are not computable. Turing's proof is not only far simpler. I mean, it's a diagonal argument, it's a clever diagonal argument. I'm sure everybody knows, but it in fact also implies the Gödel result, if you think about it, and the way most people teach. Gödel's incompleteness is via. Well, I don't know if most, but anyway, the way we do it is using Turing's notion. So that's the connection. Now, of course, Turing was inspired by Gödel's work. I mean, the whole thing that led him into working on computability was Gödel's work. So, yeah, that's a connection.
Professor Lovász?
Yeah, maybe just one thought I would like to add. The Turing machine is really just consists of two parts. It's a finite automaton and a memory. Now, if you think about it, the memory is needed. Whatever computation you do, you need to remember the partial results. So there is a memory, and the simplest way is just write it on a tape, in a string, and then the finite automaton is sort of the simplest thing that you can define, which will do will have any kind of computation. And if you combine the two, you get the Turing machine. So it's also natural from this point of view.
Now comes a really big subject, but I have some leading questions. So what is the P versus NP problem? What is it? Why is that problem the most important in theoretical computer science? And of course, prestige is enormous because it's one of the 7 clay millennium problems. What would the consequence be if P is equal to NP? How do you envisage a proof of P different from NP would require of tools? And the question goes to you, Professor Lovász.
Well, let me again go back when I was a student. I talked to Tibor Gala. He was a distinguished graph theorist and my mentor, And he said, well, you know, here are these two very simple graph theoretic problems. Does a graph have a perfect matching? So can the vertices be paired so that the pairs are connected to, each pair is connected by an edge? Or the other one is whether it has a Hamiltonian cycle. So does whether it has a cycle which contains all the nodes, the vertices. And he said that the one is well solved and there is a lot of very nice literature about it. And the other, we just have sort of superficial results. Maybe non-trivial results, but still very superficial. And so he said, well, maybe you should think about coming up with some explanation. Now, unfortunately, I couldn't come up with an explanation for that, but we tried to do with my friend Peter Gács. We were trying to find ways and to prove it, and then we both went off, and he went to Moscow for a year. I went to Nashville, Tennessee for a year. We got different scholarships, and then we came back, and then we both started to sort of wanted to speak first, because we both learned about the theory of P, NP, which completely explained this, that the perfect matching problem is in P, and the Hamilton cycle problem is NP complete. So after this, that it explains something that was a really tough question, it was clear that this is going to be a central topic. And then, of course, with the work of Karp about proving the NP completeness of lots of everyday problems, the whole theory was... So Peter Gács learned it from Leonid Levin in Moscow, and I learned it from, I not personally, but it was already discussed at coffees at conferences. So that was so I can understand. So this theory or these notions P and NP, they made such an order where there was chaos before that was really overwhelming.
Wigderson, please.
Let me speak, of course, the fact that it puts an order of things in a somewhat, the world that looked pretty chaotic is a major reason why this problem is important. And in fact, there's sort of almost a dichotomy. Almost all natural problems we want to solve are either in P, as far as we know, or are NP complete. Namely, in the two examples that László gave, perfect matching is in P. We can solve it quickly, and we can characterize it. We can do lots of, we understand it really well. And the Hamiltonian cycle problem is a representative of an NP complete problem. And the main point about NP completeness is that every problem in this class is equivalent to every other. So if you solve one, you've solved all of them. And by now we know thousands of problems that we want to solve in logic, in number theory, in combinatorics, in optimization, and so on, that are equivalent. So suddenly we have these two classes that seem separate, and whether they're equal or not, this is a P versus NP question. And we know that all we need to answer it is just know the answer for one of them, one of these NP complete problems. But I want to take a higher level point of view about the importance of this problem, and related to what I said, natural problems we want to compute. I often argue in, at least in popular lectures, that problems in NP, people fear that it's, maybe too technical to understand, are really all the problems that we human, especially mathematicians, can ever hope to solve. okay? Because the most basic things about problems we are trying to solve is that we will at least know if we solve them, right? I mean, we don't normally embark, so not just mathematicians, physicists don't try to, build a model for something if they don't think that when they find it, they will know if they found it. Or the same with, engineers with designs, or detectives with solution to their puzzles. I think that in every undertaking that we seriously embark on, we assume that when we find what we were looking for, we know that we have found it. But this is the very definition of NP. This is a problem is in NP exactly if you can check that the solution you got is correct. Okay, so now we understand what NP is. Now, if P equals NP, it means that all of these problems have an efficient algorithm. All of them can be solved really quickly on a computer. So in some sense, if P equals NP, then everything we are trying to do can be done, I don't know, maybe find a cure for cancer and serious problems. Can be, all this can be found quickly by an algorithm. So that's why it's important, but that's also, I think, to most people is the reason to believe that probably P is different than NP.
Maybe if I can add one more thought. So you asked about how can it be proved that P is not equal to NP, maybe. So there's a nice analogy here with constructions with the ruler and compass. So that's one of the oldest algorithms, exact notions of algorithms. What can you construct by ruler and compass? And probably the Greeks already, they formulated the problem like trisecting the angle or doubling the cube. And they probably believed or conjectured that it was not solvable by ruler and compass. But to prove this, that it's not solvable by ruler and compass, even today it's not easy. It can be taught in an undergraduate class, but in an advanced undergraduate class, let me say this. So you had to develop the theory of algebraic numbers, and a little bit of Galois theory in order to be able to prove this. So sometimes the problem is much simpler, but to prove that it's not solvable by, in that case, by a specific class of algorithms, takes a huge development in a completely different area of mathematics. And I expect that maybe P not equal to NP might be similar. Of course, we probably won't have to wait 2,000 years for the solution, but it will take a substantial development somewhere in some area which we may not even are aware today of.
But I take it for granted that you both think that P is different from NP, right?
I do, but I must say that the reasons we have are, are not very strong. Main reason is that what I said before is that for mathematicians, and I'm sure for you too, the very fact that it seems much easier to read proofs of theorems that were already discovered than to discover these proofs suggests that P is different than NP. And many people have tried to find algorithms for many of these NP-complete problems for practical reasons, right? Various scheduling problems, optimization problems, graph theory problems, and failed. So this failure may suggest that there is no such algorithm, but of course it's a weak argument. So in other words, I intuitively feel so, but I don't think it's a strong argument. I just believe it as a belief, a working hypothesis.
Professor Wigderson, you were born in 1956 in Haifa in Israel. Could you tell us when you got interested in mathematics, and in particular in theoretical computer science?
Sure, yeah. So of course, I got interested in mathematics much earlier. Probably as a very young child. My father introduced me to this. He liked to ask me questions and puzzles as a very young child, and seeing that I was interested, as I was growing up, he found books that I could read, and there would be more problems in there. And this was my main early interaction that in mathematics. In high school, we had a very good mathematics teacher who came from the Ukraine, and he had a special class for interested kids, and he taught us more exciting stuff like college level stuff, and I got even more excited about it. And of course, in college, I got much more into it. It's actually an accident that I got to computer science and thereby to theoretical computer science. After my army service, as I was applying to colleges in Israel, I thought I wanted to do math, but my parents suggested that maybe it's good also to have a profession when I graduate. So they said, why don't you study computer science? And, there'll probably be lots of math in it anyway, and you'll enjoy it. But when you graduate, you'll have a computer science diploma. Nobody was thinking about academia. I mean, and so, I went to the computer science department at the Technion, and I think it was extreme luck. I'm sure if I were in a math department, I would be interested in many other things, analysis, combinatorics, I don't know, geometry, so on. But because I was in a computer science department, I took several theory courses. We had, in particular, a very inspiring teacher, Shimon Even at the Technion, and his courses were, mainly on algorithms. And NP-completeness were extremely inspiring, and so I was drawn into this. That was, it was math, but math I loved doing. So when I applied to graduate school, I applied to continue doing that. So that's how I was drawn to theoretical computer science.
But still, so in another interview earlier on, you have described yourself as a beach bum and as a soccer devotee. So that contrasts rather starkly with what you're telling us now. There are two sides to you.
I don't think at all that there is a contrast. If you think about the place I grew up, I mentioned that my dad was the main intellectual contact with mathematics. Schools in this neighborhood were not very good, was pretty boring. And anyway, everything that anybody did, it's a neighborhood by the beach, so everybody was at the beach. It's not you are a beach bum by definition. And the weather in Israel is wonderful, so you can be maybe 300 days a year on the beach or in the water, right? So that was one pastime activity. The other thing, there was no soccer is the easiest, it's the easiest game to play, where you have nothing, no facilities, and that's what we did. We did a lot. So I think it was just, growing up and, being involved in these activities. I never saw myself as a kid as an intellectual. I knew I loved math, but that was one of the activities I loved. I loved soccer, I loved swimming, and I loved reading. And that's how I spent all my youth. And I don't see any contrast. I mean, if anything, it's probably good to do other things.
Yeah, actually, of course, it's been famous that you can do mathematics on the beaches of Rio. So I guess you can do it in Haifa as well. Professor Lovász, you were definitely not a beach bum. you had you were supported by the Hungarian school system in every aspect, weren't you? You followed it through.
I was until I was entering 8th grade. I didn't have any particular special subject that I was particularly interested in. The 8th grade, I started to go to a math club, and I realized that there are how interesting problems there are. And then the teacher of the math club recommended that I go to a particular high school, which was just starting there, which was specializing in mathematically talented kids. And we had about 10 hours of mathematics, 10 classes of mathematics a week, which this group of students enjoyed very much, including myself. And I enjoyed very much the fact that I was among a fairly large group of children who were, or students or pupils who were quite similar interest. And in the elementary school, I was sort of a little bit outside the sort of the cool group of the class. So I was not in the mainstream of the class, but in this high school class, I was I found myself much more at home. In fact, so much at home that I married one of my classmates, and we still are together. So this is this high school was really an absolute great start for my life. That's how I feel about it. Before that, it was, yeah, you had to survive the school, but that was so. This high school was really not only the other kids, but that was in the first half of the 60s, and there were many good mathematicians in Budapest, but they didn't really have a chance to travel or to do anything outside Hungary. So they had more time they came to the high school and gave talks to. They had great interest in this group of our group, and so we learned a lot from them. And I mean, I should of course mention Paul Erdos, who was often visiting the class and gave talks, gave problems, and so he was very inspirational there.
So, but even so, to quote actually Professor Wigderson, he says, "In the land of prodigies and stars in Hungary and its problem-solving tradition, he," that meaning you, "shone from a very early age. And I have a witness who recalls rushing home from school to listen to the final of one of the competitions in which you participated. On national broadcast, is that correct, where you solved a combinatorial problem real time? It's kind of hard to imagine here in the West that you do such things, but this was part of what you were doing."
That was one of the things that went on for a few years then. Unfortunately, then it stopped, because I thought it's a very good popularization of mathematics. I mean, not that people would want to compete. So the way it worked was that there were two glass cells, and in each there was one of two students were sitting in the two cells, and they got the same problem, and then they had to solve it, and then verbally tell the solution. Maybe there was a blackboard in the behind, and I remember that I think people like to see nice young people sweating and doing their best to win, and most people cannot jump over 2 meters, but nevertheless, we look at the Olympic Games, and so people had probably the same approach to this. And even today, I meet people, of course, older people, who say, yeah, I saw you on TV when you were in high school, and I was maybe in the 8th grade of elementary school, and it was so nice to watch you. So it's really something quite special.
Yeah. I think part of the story which makes it so fun to listen to is, or hear about, is that I think you told that the solution to the final problem that you won the competition was you had learned the solution from the other competitor. Isn't that correct?
Yes. So that was, but so we were also good friends. We still are very good friends with especially the two people whom I had the semi-final and the final one was Miklós Lackovics. He came up with the proof of Tarski's conjecture about squaring the circle, and the other one was Lajos Pósa, who is very well known in education, in math education. He did a lot in developing methods to teach talented students. So this was very good times.
Yeah, before we leave this subject, we should also mention that you won the gold medal 3 years in a row from 1964 to 65 and 66 in the International Mathematical Olympiad when you were only 16, 17 and 18 years old. That's fantastic. I don't know of anyone that has such a record in that competition. But anyway,
yeah, there are others. People have won it 4 times. Some others.
Really?
Yeah.
Okay.
You can go to the homepage of the International Mathematical Olympiad, and there is a list of achievements.
We often characterize mathematicians as theory builders or as problem solvers. Where would you place yourself on a scale ranging from 0, that is a theory builder, to 1, being a problem solver? Let's start with you, Avi.
Yeah, well, what can I say? I love solving problems. But I think it's probably true for many that if you are not satisfied just with solving the problem you had, but you immediately think of, oh, this is how I solved it. Maybe there's techniques that can be applied in other places, and you do apply it in other places, and you write it in most general forms, and that's how you present it. Then you may be called also a theory builder. So I don't know. I don't want to characterize myself. I can leave it to others. I enjoy doing both things, finding solutions to problems and trying to understand how they apply, elsewhere. I love understanding connections between different problems and more between different areas. I think we are lucky in the theoretical computer science that many sort of dispersed areas are so intimately connected, sometimes not obviously so, like with the hardness and the randomness. And so theory is built by such connections.
László?
I have similar feelings. I like to solve problems. I started out sort of under the inspiration of Paul Erdős, who was really always putting everything into breaking down the questions into problems. I think that was a particular strength of his mathematics, that he could formulate simple problems. And I don't remember who said about him that it would be nice to know the general theories that are in his head, which he breaks down into these problems that he feeds us so that we can solve them, and therefore, and indeed, based on his problems, whole new areas arose, extremal graph theory, random graph theory, probabilistic combinatorics in general, and also various areas of number theory. So I think I am a little bit so that I started out as a problem solver, but I always like to also make connections and try to build something more general on a particular problem I have solved.
Okay.
We'll continue to Professor Lovász. A following question. You have published several papers with your mentor, Paul Erdos. I think 6 papers altogether. And I could ask you, of course, which one of these is your favorite, but I think I have the answer to that, and you can correct me if it's not correct. Namely, the term Lovász local lemma. First of all, tell us what it's all about. And apparently a weak version of this was proved in 1975 in a joint paper with Erdos. So that's why I think this maybe is your favorite paper, probably Erdos. And the lemma is very important, and to attest to that importance is that Kneser and Tardos, I don't know if I pronounce it correctly, received the Gödel Prize in 2020 for their algorithmic version of the Lovász local lemma. Anyway, could you tell us what the Lovász local lemma is all about?
Okay, I'll try. If you have a lot of events, I mean, almost everything in mathematics you can, or at least in discrete mathematics, you can formulate like there are a number of events that are bad events, and you want to avoid all of them. And then the question is, can you give a condition under which you can avoid all of these? So the most basic thing is that if the probabilities of these events add up to something less than 1, then with positive probability you avoid all of them. That's a very basic trick in application of probability in discrete mathematics. But now suppose that their number is much larger, so the probabilities add up to something very large. Another special case when you can say it is if they are independent events. Then if you can avoid each of them separately, then there is a positive probability that you avoid all of them. Just simply the product of the probabilities that for each of them that you avoid that. And the local lemma is some kind of combination of these two ideas. If the events are not independent, but each of them is dependent only on a small number of others, then you can still have this chance, so that if the sum of the probabilities of those that it depends on is less than 1, not the total sum, but just those, then you can still with positive probability avoid each of those. And maybe I should add one thing here, is that there was a problem of Erdos which I was thinking about. I came up with this lemma. We were together with Erdos at actually Ohio State for a summer school there. And so I was And so it solved the problem, and then we wrote a long paper on that problem and related problems, including this lemma. But Erdos, who realized that this lemma was sort of more than just a lemma for this particular problem, he made sure that it was it became known under my name. So normally it would be called Erdos-Lovasz local lemma, because it appeared in a joint paper of us. But he always promoted young people. He always wanted to make sure that for young people, if they had something, then it became known. And so that was that was one of these things that, of course, I benefited from his generosity.
In 1955, Kneser conjectured how many colors you need in order to color a type of naturally occurring graphs known as now as Kneser graphs. In 1978, you, Lassi, proved the Kneser conjecture by encoding the problem as a question of high-dimensional spaces, which you answered by using standard tools in homotopy theory. And by doing so, you boosted the field of combinatorial topology. How did such a line of approach occur to you? And can you say something about the problem and your solution?
Very briefly, but it goes back to one of these difficult problems, the chromatic number problem. How many colors do you need to color a graph properly, where a proper means that the neighboring points must have different colors? And that's a difficult problem in general. It's an NP-complete problem. And one of the first approaches is that one looks at local structure. So if a graph has many points which are mutually adjacent, then of course you need many colors. And the question is there always such a reason? And it was already known at that time that there are graphs which have absolutely no local structure, so they don't have short cycles, but nevertheless you need many colors to color them. But it was an interesting question to construct such graphs, or maybe just exclude triangles, or exclude, somehow it's easier if you exclude odd cycles from the graph. And there was a well-known construction for such graphs by looking at the sphere and then connecting 2 points if they are almost antipodal, and then Borsukh's theorem says that you need more colors than the dimension to color it so that these almost antipodal points have different colors. So that was one construction, and the other one was a construction where the vertices will be the k-element subsets of an n-element set, where n is larger than 2k, and you connect two of these if they are disjoint. And Kneser conjectured what would be the chromatic number of such a graph. It was an interesting problem. Going around in Budapest, and actually Miki Simonovic, one colleague of mine, he said, well, he called actually my attention that these two problems are sort of similar. The two constructions, are they similar? And so I came up with a reduction of one into the other, but then it turned out that the reduction was more general, and it gave a lower bound on the chromatic number of any graph in terms of some topological construction. So that's how topology came in, and it took actually quite some time to make it work, but I remember I spent about 2 years to make this idea work, but eventually it worked.
But the idea of using Borsuk-Ulam, that was circulating in the community already to similar problems.
Yeah, that the Borsuk-Ulam construction has similar properties than the Kneser construction. That was circulating, yes. To reduce one to the other maybe was not explicitly formulated, this idea, but it was in the air.
Mm-hmm. By the way, I will secure that we have a Kneser graph in the printed version that people can look at.
Avi, early in your career, You made fundamental contributions to a new concept in cryptography, namely the zero-knowledge proof, which more than 30 years later is now being used in blockchain technology. Please tell us more specifically what a zero-knowledge proof is and why this concept is so useful in cryptography.
Yeah, that's one of the easiest things to explain. So for mathematicians in particular, so suppose you found a proof of something, like the Riemann hypothesis. And you want to convince your colleagues that you have found this proof, but you don't want them to publish it before you do. You just want to run it by them, but you are worried that they, for some reason, you just want to convince them only of the fact that you have a proof of this theorem and nothing else. It seems ridiculous. It seems absolutely ridiculous, and it's contrary to all our intuition that there is a way to convince someone of something they do not believe without giving them any, shred of new information. But it's this very, idea that was raised by Goldwasser, Micali, and Rakov in '85, where they suggested this notion. Now, they did not suggest it for paranoid mathematicians. They suggested it for cryptography. They realized that in cryptography, there are lots of situations, in fact, almost all situations in interaction between agents in a cryptographic protocol that no one trusts the other one, and nevertheless, each of them makes claims that they are doing something or they are knowing something which they don't want to share with you. For example, their private key in a public key crypto system, right? So, each one is supposed to compute their public key by multiplying two private numbers, which they keep secret. So I give you a number, tell you, okay, here's a number. I multiply two secret prime numbers and this is a result. Why should you believe me? Maybe I did something else and, this is going to ruin the protocol. To fix this, it would be nice, as they said, if there was a way for me to convince you that that's exactly what I did, namely, that's a theorem, right? There are two prime numbers whose product is the number I give you. It's a mathematical theorem. I want to convince you of it without giving you any idea what my prime numbers are or anything else, okay? So they suggested this notion as an extremely useful notion if we could have it. And they gave a couple of non-trivial examples which were related already to existing crypto systems where this might be possible. And they asked the question, what kind of mathematical statements can you have a zero knowledge for? It looked extremely special. And so a year later with Silvio Micali and Oded Goldreich, we proved that it's possible for any mathematical theorem. If you want it formally, it's true for any NP statement, anything for which there is a short proof. So this is the content of the theorem. I'm not going to tell you the proof of this theorem, although something can be said about it. And the proof uses cryptography essentially. It's a theorem which assumes the ability to encrypt. So that's the content of the zero knowledge theorem. Why it's useful in cryptography is exactly why I described, but in fact it's much more general, as we observed in a subsequent paper. Given zero knowledge proofs, you can really automate the generation of protocols that are safe against bad players. Once you have a protocol that works, if everybody is honest and doing exactly what they should, because the way to get protocols that are resilient against bad players, if you have one that is just working fine when honest players, is just to intervene every step with a zero-knowledge proof in which the potentially bad player will convince the others that it is doing the right thing. It's much more complex than that. Zero knowledge is not enough. You have to have a way of computing with secrets, but let me not go into that.
It's an amazing result, and I think that you have said that probably the most surprising, the most paradoxical of the results I have proved, which I can really appreciate. Let me continue, Avi, with the following question to you. When you began your academic career in the late 1970s, the theory of computational complexity was in its infancy. Your contribution to enlarging and deepening the field is arguably greater than of any single other person. We want to focus here on your stunning advances in the role of randomness in aiding computation. You showed together with co-workers Nisan and Impaglicio, it's difficult to pronounce, that for any fact algorithm that can solve a hard problem using coin flipping, there exists an almost as fast algorithm that does not use coin flipping, provided certain conditions are met. Could you please elaborate on this and be a little more specific?
Yes, but let me just add one sentence on the zero-knowledge aspect. I want to stress that when we proved this theorem, it was a theoretical result. It was clear to us from the beginning that the protocol which enables zero-knowledge proofs is complex, and we thought it unlikely to be really used in cryptographic protocols that are running on the ground, on the machines and so on. And it still amazes me that people manage to transform them to much more efficient protocols that are being used, both these protocols and others. So the fact that it became practically useful is still an amazing thing to me, and I think that's a good point to say about many other theoretical results in theoretical computer science, in particular about algorithms. People tend to complain sometimes about the notion of P as being too liberal when describing efficient algorithms, because some algorithms where they are first discovered may have a running time that looks too large. It's a polynomial time, but maybe it's n to the 10th power, and n to the 10th for size 1,000 or size 1,000,000, which are problems that come up naturally in practice. It seems just useless as exponential. And what you learn, and again, both in the field of cryptography and in the field of algorithms, is that once you have a theoretical solution with ideas in it that make it very efficient, then other people, especially if they are motivated enough, like in cryptography or in optimization, you can make it then much more efficient and eventually practical. So that's a general point I want to make. Okay, so now let me return to your question about randomness. So randomness has always fascinated me, the power of randomness in computation, and not only in computation. And this is probably the area I invested the most time of my research, apart from, I would say successful part of my research. The other part would be trying to prove lower bounds or hardness results, in which I, generally, like everybody else, failed. Like proving that P is different than NP. So what you're trying to understand is the following. Ever since the 70s, people realized that randomness is an extremely powerful resource to have in algorithms. There were initial discoveries like the primality test. So Strassen and Rabin discovered fast methods with randomness to test if a number is prime. And also encoding theory, Berlekamp, and number theory, and then many others all over the place in graph theory and optimization and so on. People just realize it's extremely powerful. There are problems we have no idea how to solve without randomness efficiently. And nevertheless, with randomness, you can find the solution very fast. Another famous class of examples is Monte Carlo methods, right? So you explore a large space using randomness, and without it, it seems like it would take exponential time. So the power was realized, and it was natural to believe that yes, having randomness is much more powerful than not having it. Nevertheless, mainly from motivations in cryptography, people started in computational complexity trying to understand pseudo-randomness. You need randomness in cryptographic protocols for secrecy and so on. And on the other hand, sometimes random bits were not so available, and you wanted to test when are random bits good as like having really independent coin flips, which you really assume when you are talking about probabilistic algorithms. So there was a quest to understand when is a distribution, let's say, of bits is as good as random. So this started in cryptography with the very powerful works of Blum and Micali and Yao, and notions began to emerge which suggested that if you have computational hardness, if you have some hardness assumption, if you have a hard problem, then you can generate pseudo-random bits cheaply. So you can invest much less randomness in order to generate a lot, which is still useful, let's say, for probabilistic algorithms. So this kind of understanding, which started in the early 80s, it took about 20 years of work to really elucidate it and be able to make the weakest assumptions on what hardness you need in order to have a pseudo-random outcome, which will then fool probabilistic algorithms. Part of it was indeed developed in my papers with Nissan, and then with Baba and Fortnow, and then with Impagliazzo and with Cabanets. The upshot of this development is, again, it's a conditional result, right? So it's you have to assume something if you want the conclusion you stated. What you need to assume is that some problem is difficult. You can take it to be the problem of coloring graphs, or you can take it to be any NP-complete problem you like, or even problems that are higher up. But you need a problem that is exponentially difficult. This is an assumption that the result is conditioned on. It's and if you are willing to make this assumption, then the conclusion is exactly as you said, that every efficient probabilistic algorithm can be replaced by a deterministic algorithm which does the same thing, in fact without error, and is roughly as efficient as the original one. So, in other words, the power of probabilistic algorithms is just a figment of our imagination. It's only that we are unable to find deterministic algorithms that we can prove are as efficient. This result suggests that, there is no such power. Randomness doesn't help in making efficient algorithms more efficient.
The hardness assumption that you need to make, was that something that you were expecting, or did that come as a surprise to you as well?
completely expected. First of all, it is expected in the sense that it was there from the beginning. The works of the Blum, Micali, and Yao papers that I mentioned, which do create pseudo-random generators that are good against efficient algorithms, assume specific hardness assumptions like those used in cryptography, for example, that factoring is difficult or that one-way functions exist. These are very specific hardness assumptions. These problems are unlikely to be NP-complete. And in my paper with Nissan, we realized that a much weaker assumption is enough. It was not enough to give the result stated at the end because it's not efficient enough, but it already got us pretty close to the understanding that random algorithms are not as powerful as they are. It didn't give the BPP equal P consequence, which is the sort of the final one, but it was not surprising. This was the connection, this paradigm between hardness and randomness came from the very initial studies of computational pseudo-randomness. And if I remember correctly, the paper of Blum and Micali, or maybe the PhD thesis of Silvio Micali, is titled Hardness versus Randomness. So yeah, there's an intimate connection there. It was there from the start, and the question is how tight is the connection? I should probably mention that the consequence we just discussed is hardness implies randomness, and the question is whether the reverse holds also. If you have a good pseudo-random generator, or if you could de-randomize all probabilistic algorithms, does it mean you can prove something like P different than NP? And the answer is that we have partial results like that. The paper with Impagliazzo and Cabanet is one. There's another paper of just the two of them. That is another. There are partial results in the converse, and we don't understand it fully, but it's a fascinating connection because these two issues seem separate from each other. So that's, I think it's a very fundamental discovery of the field, this intimate connection between computational difficulty and the power of randomness.
We also, of course, want to talk about the LLL algorithm, an algorithm which has striking applications. For instance, it is claimed that the only cryptosystems that can withstand an attack by a quantum computer use LLL. So the algorithm appears in a paper together with the Lenstra brothers on factorization of polynomials, which more or less follows the expected path of reducing modulo primes and then using Hensel's lemma. But as far as I understand, the breakthrough of László here and the Lenstras was that you were able to do the lift in polynomial time by an algorithm giving you an approximation to the shortest vector in a lattice. How did the collaboration with the Lenstras come about?
This is actually an interesting story about mathematics and the role of sort of beauty or at least elegance in mathematics. So with Martin Grötschel and Lex Schreiber, we were working on applications of the ellipsoid method in combinatorial optimization. And that was, we came up with some general theorem state, it's called equivalence of separation and optimization, so that for a convex body you can these are polynomial time equivalent problems under some additional conditions. But there was a case where the algorithm, the method didn't work, and that was when the convex body was lying in a lower dimensional linear subspace. And one could always get around this, sometimes by mathematical methods, focus on that lower or map everything into that lower dimensional subspace, sometimes by blowing up fattening the, but they were always ad hoc tricks. So we wanted to get something, and so at some point I realized that we can solve this if we can solve some really ancient mathematical problem algorithmically. And that was Dirichlet's result that several real numbers can be simultaneously approximated by rational numbers with the same denominator. If you could solve this algorithmically. Now one looks at the proof and one sees immediately that the proof is the opposite of being algorithmic. It's a pigeonhole principle proof, so it just shows the existence of such an approximation. And then after some trial and error, and I came up with an algorithm which actually computed in polynomial time such an approximation with rational numbers with common denominators. And then I wrote a little bit earlier I heard a talk of Henrik Lenstra, where he sort of talked about similar problems, but in terms of lattices and basis reduction in lattices. So I wrote to them, and it turned out that they had a proof that if you can do this, this is a little bit the shortest lattice vector problem, which it is easy to reduce the Dirichlet problem to a shortest lattice vector problem. So if you can solve this, then they can factor polynomials in polynomial time, which was actually surprising because one first would think that if you want to factor, then factor an integer should be easier than factor a polynomial. But it turns out that it's the other way around, and polynomials can be factored in polynomial time. So that's how this joint paper came about, and in about another couple of years, then Lagarias and Odlyzko discovered that this algorithm can be used to break the so-called knapsack cryptosystem. And since then, this algorithm is used a lot in checking the security of various cryptosystems.
Yeah, as far as I understand, it has wide applications, way beyond anything that you perhaps imagined.
Yeah, definitely. Yeah, so shortly after it was published, it was used in a very extended numerical computation to disprove the so-called Mertens conjecture. I think it was Odlyzko and Terile. And so this is a number theory, in prime number theory, about zeta function. So altogether, it's it had a lot of. So the point is why I wanted to tell this is that the whole thing started from something that was really not so important. We just wanted to get the nicest possible theorem about equivalence of optimization and separation. And this is good enough motivation in mathematics to make something nicer.
But as far as I understand, you kept improving your method constantly during a process together with, or while you were talking to the Lenstras?
Not that much, actually. Not that much. I mean, there was this extension from the Dirichlet problem to lattices, but that was a well-known connection. Other people, of course, worked on it. I have not worked on improving this.
Again, László, this is a question to you. In 1981, you published a paper together with co-authors Gretschel and Schreiber. I don't know if I pronounced the names correctly, titled The Ellipsoid Method and Its Consequences in Combinatorial Optimization, a paper which is widely cited. There is a prehistory to this, namely a paper by a Russian, Kashigan, I don't know if I pronounced that correct either, containing a result that was regarded as sensational. Could you comment on this and why your joint paper is related to his?
He published a paper. He gave the first polynomial time algorithm for linear programming using what's called the ellipsoid method today, which was actually, I should say that was in the Soviet Union in the air. There were several other people who worked on similar results, but he applied it and probably proved the necessary details that to come up with that was Khachiyan who proved that linear programming can be solved in polynomial time. Of course, everybody got interested. Linear programming before that was one of those little bit mysterious problems that in practical terms could always be efficiently solved, but there was no polynomial time algorithm known to solve linear programming. And so we got interested in it, and we realized that to apply Khachiyan's method, you don't have to have an explicit description of the linear program. It is enough if the linear program is given in such a way that if you ask about a point, whether it satisfies, whether it's a feasible point, then you should be able to tell this, and you should be able to find the constraint which is violated, if any constraint is violated. That observation was made by several people, also by Karp and Papadimitriou, and I think Padberg and Rao. So, we realized that in combinatorial optimization there are many situations like this. And then I met Martin Grötschel, and he came up with a way to apply this method to, it's another old problem, to find the chromatic number of a perfect graph, which was also an unsolved problem in those days, whether it can be found in polynomial time. And for that, it turned out that you had to apply this ellipsoid method not only to linear programs, but to convex programs more generally. And so the three of us with Lex Schreiber, who actually was a roommate or office mate of me, he visited Szeged for a year, and we shared an office and we worked on this. And so we started to see what happens in general in convex optimization, how to apply this. And that's how we came up with this result that I mentioned, that the equivalence of separation and optimization, it was sort of the main outcome of these studies. Eventually we wrote a monograph about this subject.
Oh, this is such a hard thing because you have so many wonderful results between you. But I do want to talk about the zig-zag graph product. Can I, or can we? So expander graphs, of course, they have, and constructions of expander graphs, they have had a recurring theme for the Abel Prize. So last year we had Margulies, who gave the first explicit expander graphs after Pinsker had proven that they existed. And Gromov, who won the Abel Prize in 2009, used expanders on Cayley graphs on fundamental groups, which led to a study of the Baum-Kohn conjecture, and of course Ceremere in 2012. Who, as far as I understand, Avi, you have some papers together with Ceremere, isn't that right? But not on this.
On this, yeah, they are, yeah, no, it's not on.
So, but you, together with Reingold and Vadan, presented the zig-zag product on regular graphs, which is, as far as I understand, analogous to the semi-direct product in group theory, and by which you gave explicit constructions of very large and simple expanders. Could we just start? What is the zig and what is the zag?
So first, maybe I should start with what is an expander graph.
Brilliant.
You should think of networks, and you should think that one desirable property of networks is that there will be sort of fault tolerant, will be able to be very connected, and if some of the connections are severed, you will still be able to communicate. It can be networks, on the internet or network on the computer networks. Can be also networks of roads. You would like to be highly connected, and if something, anyway. And of course you don't want to pay, so you would like these networks to be sparse. You don't want to have too many connections. So you want a large graph in which the degree of every vertex, the number of connections of every vertex is small, let's say a constant, maybe 10. Okay, so a random graph will have this property, and the whole question, this is what Pinsky realized, and then the whole question is, can you describe such graphs? Can you build them efficiently? And indeed, Margulis gave the first construction using this deep algebraic concept, the Kashdan-Tau property, and they can be built from Selberg's number theoretic results. And then people started simplifying the proofs. By the time I was teaching this material, there were reasonably simple proofs like Jimbo and Maruka, where it's just, you could teach it in a class of an hour or two. It just basically goes down to a Fourier transform in finite groups. So you have everything you want. You have a very nice explicit construction. You can prove it in a class to even undergraduates, and but to me it was this, like many algebra proofs, mysterious. I mean, what's going on? I mean, what is really driving the fact that these are highly connected graphs? Why don't they have the small cuts? What's really? And this was sort of an obsession of mine for years, but I didn't know what to do with it. Then in the year 2000, I had two postdocs here, just after I moved to the institute, Salil Vadan and Omer Reingold, and we were working on a completely different project, part of the big pseudo-randomness project, where another important notion is the notion of an extractor, something to purify randomness. I will not talk about it now, but we were trying to build better extractors. And as we were doing this, we realized that one of our constructions may be useful towards creating expanders. And the constructions in the extractor business were often iterative and had a very different combinatorial nature than constructions, let's say, of the algebraic type. And once we realized this, we understood that we have a completely different combinatorial construction of expanders, and not just combinatorial, one in which, for me at least, it was clear, it was evident from the proof why these graphs are expanding. This is the result. The zigzag is just, there was actually a name suggested by Peter Winkler. If you look at the construction starts with a small graph which is expanding, something of constant size, something you can have anyway, and just uses it to keep boosting another graph to being expander. You get an expander, then you plug this little graph in somehow, and you get a bigger one, and then you get a bigger one, and so on. So you can generate arbitrarily large expanders. This local construction has some zigzag picture in it. If you look at it, that's not the important thing. I would say that maybe the way the intuition reveals itself in the property of expansion. It's just when you think about another way of describing an expander. An expander is a graph where no matter what distribution you have on it, just distribution on the vertices of, if you take this distribution, you take a vertex from this distribution and apply, you go from this vertex to a random neighbor, the entropy increases of your distribution, if there is room to grow, of course. That's another way to describe expanders. And this you see almost with your eyes in the zigzag construction. You see how the entropy grows, and that's what I like about it.
But so to have the picture, as far as I understand, so you take a small graph, or you have a graph, and then you place this other graph at all the nodes. And then then you have to decide, how am I going to put the edges in? And then essentially, and here you must correct me because I don't know what I'm talking about, but what essentially you're doing is that just like in the product of the semi-direct product, when you have the multiplication rule, you move a wee bit in one of the nodes, then you jump all the way to the next node, and then you do the similar jump there. Is that correct, vaguely?
It's completely correct. And moreover, this connection to semi-direct product is something we realized like 2 or 3 years later with Alex Lubotsky and Noga Alon. So it was a sort of challenge which I felt early on. These graphs that we got were expanders, compilatorially generated, simple, we understood them, everything was good. And I was wondering whether it can be useful to construct Cayley graphs, because such constructions existed, and it was just curiosity. And then with Noga Alon and Alex Lubotsky, we realized that actually it's not just similar. The zigzag product is a combinatorial generalization of semi-direct product of groups applied to Cayley graphs. So it's a more general. It just specialized in the case of Cayley graphs to semi-direct product. Anyway, because of this, for example, you can prove that Cayley graphs of groups that are not simple can be expanding with a constant number of generators. This is no algebraic method is known to give this. Yeah.
And so you actually. So I'm amazed that you got this formulation for the zigzag product without previously having the intuition from the semi-direct product. That's truly amazing.
It came from an extractor construction, which was So I agree. It is strange to me. It was strange that there was a connection to algebra.
But of course, this has been used extensively in many situations, and of course, one of the things one perhaps should mention is that the symmetric log space and the log space, Rheingold in 2008, that they are the same. This seems to have been an idea that really caught on. Are you still using it yourself, or have you let your baby grow up and run into the mathematical community?
I think it's great that we have a mathematical community. Many ideas I had were taken to places beyond my imagination. There's something fundamental about this construction, and it was used, like you said, in this Rheingold result, which can be more simply described as a log space algorithm for just connectivity in graphs. In fact, it goes back to a result of László and his collaborators and can be viewed as a pseudo-randomness, as a derandomization result. László in 1980 with Karp and Aleliunas and Lipton and I forget who else, showed that if you want to test whether a large graph is connected, but you have no memory, you have just enough memory to remember where you are, then by tossing coins, you can explore the whole graph. Okay? This is the result. It's a random log space algorithm for graph connectivity. And Derandomizing this algorithm was another, pet project of mine that I never got to do. But Reingold observed that if you take the zigzag product and apply it very cleverly to their algorithm, to their randomized algorithm, you get a deterministic log space algorithm for the same problem. So it's a particular pseudo-random generator tailored to this. It was also used in the new PCP theorem of Irid-Dinur. There is something general in this zigzag product that other people found extremely useful.
Actually, this brings us to an interesting place in this interview, because here we are seeing connection between what the two of you are doing. Would one of you care to expand on the connections between the mathematics of the two of you?
Well, let me see. You see, you didn't tell us who to start, so let me just mention one of the most influential things that happened to me in my postdoc years. It was in '85. I was a postdoc at Berkeley, and there was a workshop in Oregon in which László gave 10 lectures. I don't remember exactly what it was called, on the lectures on optimization, the geometry of numbers. And so the kind of point of view I got from this type of event was a whole week of lectures. Anybody who heard László talk knows, just how extremely clear everything is. But one thing I got out of this is what László described when you asked him the previous questions about the LLL algorithms and the work on the ellipsoid and so on, is how a high-level point of view, rather one focused on a problem, rather a high-level point of view, can connect lots and lots of areas of mathematics of great importance. I mean, you saw, and László described it before, how a question that was a bit particular about just having a more elegant solution to a problem in optimization led to, just solving the lattice basis reduction problem, and how it connects to the Diophantine approximations, and how it connects to cryptography, and how it connects in cryptography both to breaking crypto systems and creating crypto systems. And, you get this panoramic view where everything fits with each other. I was extremely influenced by this. This was, an amazing, memorable event in my early career.
I think I have some similar memories, like zero knowledge proof was such a shockingly exciting thing that I learned about, and it sort of showed me how powerful these new ideas of cryptography and computer science, theoretical computer science in general, how terribly powerful they are. I think I was always very interested in Avi's work on randomness, even though I was sometimes trying to go the opposite direction and find examples where randomness really helps. Now, one has to add that this is sometimes a matter of the model, of the computational model. So I mentioned some results about convex optimization, convex geometry, algorithmic results in high-dimensional convexity. And there's a basic problem there, that if you have a convex body, how you compute the volume. And one of my was a PhD student at that time, came up with György Elekes, he came up with a beautiful proof showing that you need exponential time to approximate this volume even within a constant factor. That was in our model of in which we formulated this equivalence of optimization and separation. So the convex body is given by a separation oracle. And then a few years later, and that actually refers back to another thing that Avi said, that Dyer, Fries, and Cannon came up with a randomized algorithm to compute the volume, to approximate the volume in polynomial time with arbitrary small relative error. But their algorithm took, I mean, the interesting thing is the dependence on the dimension. If the dimension is n, then their algorithm took n to the 29 steps. So obviously it was very far from being practical. And but that started a flow of research. I was also part of it. I really liked this result, obviously, and I was quite interested in making it more efficient and understanding what are the why does it go that high up. And then then the exponent went down nicely from 29 to 17 to 10 to 7 to 5 to 4. It stood for a long time to 4, and I think a year ago or somebody it went down to 3. So now this is close to being practical. It's still n cubed is still a sort of not a really fast algorithm, but it's definitely not ridiculous. So this idea, two things. So in this example, because it's a different computational model, provably randomness helps. It's provable that without randomness it takes exponential time, and with randomness it's now down to a decent polynomial. And the second is that really polynomial time is an indicator of that this problem has some deep structure, and then you explore this deep structure, and eventually you can improve the polynomial time to something decent.
We are going to end this section on your work very soon, but I am going to ask you, László, about two results of yours. Well, anyway, we don't have time to go through all of them, so I have to select. I would love to have asked you about what is a limit theory for graphs, and what are good limits good for, and also what a graphon is, and so on. But the question I have selected, and you are free to take the other one, is that about the Shannon capacity, because in 1979 you published a widely cited paper titled On the Shannon Capacity of a Graph. In this paper you determined the Shannon capacity of the pentagon by introducing deep mathematical methods. Moreover, you proved that there is a number, now called the Lovász number, which can be computed in polynomial time, which is an upper bound for the Shannon capacity associated to a graph. Could you tell us a little more about that and elaborate on, and tell us also what the Shannon capacity is?
Okay, so I won't give a formal definition, but the Shannon capacity is that you have an alphabet and you are sending messages composed of the letters of this alphabet. But certain letters are confusable or confoundable, so they are not necessarily clearly distinguished by the recipient. And you want to pick a largest subset of words which can be sent without the danger of confusion. So for any two words, there should be at least one position where they are clearly distinguishable. And so if now the alphabet is described by a graph where an edge means that those two letters are confusable, and Shannon came up with this model, and he determined the capacity. The capacity is if you are sending very long words, then how many words you can send, and that grows exponentially, and the base of this exponential function is the Shannon capacity. And the pentagon was the first one for which this was not known, and I introduced some technique called orthogonal representations, which enabled me to answer this question. It is again one of those things that you answer a question and then all of a sudden it begins to have its own life. It was used, which I mentioned before, that to determine the chromatic number of perfect graphs. And maybe it's interesting to mention that recently some group of physicists found some, I think, quite interesting applications of it in quantum physics. So this is one of those examples where all of a sudden you hear that something you did has inspired other people to do something really interesting, and that's a very nice thing to have.
Okay, so here is a question to you, Lassi. What is a limit theory for graphs, and what are graph limits good for? On that subject, explain what a graphon is, please.
Okay, so if you want very short, maybe too technical, but I will try to be not too technical. So imagine the graph is often given by an adjacency matrix. So you can imagine it as a 0-1 matrix. And now suppose that the graph is getting bigger and bigger and you get this sequence of matrices, and we always think of these as functions on the unit square, which is cut into small squares, each square carrying a 0 or a 1. And now these functions, in some sense, tend to function which may be continuous or anyway not discrete anymore on the unit square, and that's a graphon. So for example, if the graph is random, so each square is randomly 1 or 0, then it will tend to a gray square identically 1/2 graphon. So that's a function. A graphon is a function on the unit square, which is measurable and symmetric. And it turns out that you can exactly define what does it mean that a sequence of graphs converges to such a graphon. And a lot of properties of the graph are sort of preserved. If all the sequence has this property, then the limit will also have this property. So for example, if all these graphs have some good eigenvalue gap, then the limit will have a good eigenvalue gap, just to refer back to expanders. Although this is all about dense graphs. And so you go up to this space of graphons, and then of course you have to prove, and that's there are lots of technical details there, that the space of graphons in an appropriate metric is compact, which is very convenient to work with, because from then on you can so for example, if you take a graph parameters, maybe, I don't know, density of triangles, this has a limit, so it can be defined in this limit graphon. What's the density of triangles? And then in this limit graphon, there will be a unique graphon, or at least there will be a graphon which minimizes, say this, under certain other circumstances. So you can play the usual game which you play in analysis. That is the minimum, the minimizer, and then you try to do the minimizer to determine whether it's a local minimum or a global minimum. So all these things that you can do in analysis and you can do in this setting, and this all has some translation back to the graph theory.
So my last question to you concerns what is called, and this is a result from 1972, called the Erdos-Faber-Lovasz conjecture. How it came about, and your initial thoughts on how difficult it would be to prove it. And this is what we said before the break, that has it now been proved? Question mark. I also should add that apparently Erdos considered this to be one of his 3 most favorite combinatorial problems.
The background for this problem was that there was a meeting in August 72 at Ohio State, where we discussed hypergraph theory, which was just beginning to emerge. The idea is that if you have a graph, then an edge has always 2 endpoints. But you can instead look at structures where an edge has 3 endpoints or 5 endpoints and so on. These are called hypergraphs. And the question was, given any particular question in graph theory, chromatic number, connectivity, all sorts of things, how can this be generalized to these hypergraphs? And one of these questions was what's called the edge chromatic number or chromatic index for graph theory. It's a well-known variant of the chromatic number problem here, in which case you color the edges, not the vertices, and you want that edges incident with the same node should get different colors. And then you can ask the same question about hypergraphs and what upper bound you can give on that. And we came up with this observation that in all the known examples, the number of nodes was an upper bound on the number of colors needed to color the edge color the hypergraph. And but that was already a few weeks past this meeting, and I was visiting Boulder, the university in Boulder, and so was Erdos, and Vance Faber gave a party, and we were beginning to discuss mathematics, as mathematicians do usually at a party. And so we came up with this question. And Erdos did not really believe this question, that it's true. I was more optimistic. I thought maybe it will be true. It's a nice conjecture. The number of nodes is always, that many colors is always enough. And then we realized that it has some non-trivial special cases, like something called the Fisher inequality in the theory of block designs, and that's where we got stuck, and it became more and more famous. It's a very elementary question, very simple to ask, and nobody could actually get a good grip on it. Eventually, Jeff Kahn was able, maybe 10 years ago or so, I don't remember the exact date, was able to prove it with a factor of 1 plus epsilon for every positive epsilon. And a year ago, this was Daniela Kuhn and her students who were able to prove it, at least for every large enough n, but that's this peculiar feature of these conjectures, that you make a conjecture based on small n, then you can prove it for very large n, And, and what's in between is often remains like a question mark. But she gave a talk about it at the European Congress a couple of months ago, and it was very convincing. So I think it's now proved.
I would like to ask, or if you have any comments. In January 2020, 4 people, and again pronunciation of these names are not correct probably, G, Natarujan, Vidic, and Yen announced the result in quantum complexity theory that implies a negative answer to Kahn's embedding problem in operator algebra theory. As I'm very familiar with the Kahn embedding property or problem, because I work in operator algebras, this to me is a stunning thing that really quantum complexity theory can prove a theorem which has seemingly nothing to do with the complexity theory. So, sort of bringing us back to when we started this interview, it seems like the connection between, call it core mathematics or traditional mathematics, and complexity theory is, well, it's an example that they are not two entirely universes, there are connections here. Do you have any comment to that?
Yeah, I've been, ever since this result came out, I've been given popular lectures about the evolution of, the particular field that's relevant to this result, namely interactive proofs. The evolution of this area of interactive proofs, and eventually the study of quantum interactive proofs, and how it connects to this MIP star equal RE result, and to the particular questions like the Kahn's embedding conjecture and the Tselson problem in quantum information theory. And, of course, every particular result may be surprising, but I'm not at all surprised by this connection. By now, we have lots and lots of places all over mathematics where ideas from theoretical computer science, algorithms, and of course discrete mathematics are present and reveal their power. But in that particular case, I think that, well, maybe in many cases, the point of view of computational complexity, so I'm not going into the connection, but I will just say, the connection to operator algebras, to von Neumann algebras, is not so mysterious, because quantum measurements are just applications of operators, and the question of whether these operators commute is fundamental in the understanding both of quantum information theory and in the power of quantum interactive proofs. So the connection is not that surprising. I would more focus on the reason that possibly proofs could be obtained in the realm of quantum interactive proofs, and maybe not in classical quantum information theory. And this is again, it's basically the sort of tradition and vocabulary and ethos of computational complexity of classifying everything, classifying problems, classifying algorithms in classes of equivalent, of roughly equivalent resource allocation. This allows generalization, reductions between various problems, and so on. If you look at the formulation of quantum interactive proofs, and you compare them, these particular ones, these MIP star ones of multiple provers, and you compare them to the EPR paper, the Einstein-Podolsky-Rosen experiment, famous experiment testing quantum mechanics, you see the same picture. You see there a two-prover interactive proof like you see it in the more recent complexity theoretic quantum interactive proofs. You see the same pictures. But you look at the history of studying such experiments or proofs, in the physics world, the focus was on particular, different type of problems, like, those are several famous ones, and the Bell inequalities, and there are many examples of such tests of quantum mechanics. As the main study is of particular problems, whereas very naturally for people studying quantum interactive proofs, they study them as a collection. There is a collection of games, all games reducible to each other. And the proof that MIP star equals RE is a sequence of amazing reductions and amplification results, and using various quantum coding theory techniques and so on, even PCP techniques, to build a better understanding of how they behave as a whole. And I think that's the source of the power. And I think the application comes from the final results, just because the objects of study are operators on a Hilbert space.
Avi, you are currently working on something that appears to me to be quite different from what you've been working on earlier. I may be wrong here, but you call it non-commutative optimization, and it seems to me that you're doing optimization in the presence of symmetries by certain non-commutative groups, general linear groups and stuff like that. It seems like a truly fascinating project from many points of view, with connections in many places. Would you care to comment a wee bit on what you're doing here?
Yeah, so first of all, it's completely true that it's very different than anything I've done before, because it's more about algorithms than about complexity. And even more, it's using far more mathematics that I didn't know in compared to previous projects that so I had to learn, and I still have to learn much more mathematics, especially invariant theory and representation theory, and some algebraic geometry that is, I certainly was not aware of and never needed. So, it's just a general point about the connectivity of mathematics, and in particular the connectedness of algorithms, or what is used for efficient algorithms and for results in discrete mathematics from different areas of mathematics, and of course the other direction as well. It started from something that's very dear to me, from a derandomization project that been thinking about for 30 years. One of the simplest problems which have a probabilistic algorithm that we don't know a deterministic counterpart, I mean without assumptions, we don't know that, is the testing of algebraic identities. So algebraic identities, you can think about the Newton identities between symmetric polynomials, or you can think about the van der Monde identity, and there are plenty, lots and lots and lots of algebraic identities in mathematics, and we all seek them. And if anybody conjectures one, what do you do? How do you check it? Well, there's a sure probabilistic way. I mean, you just think about these are polynomials with many variables. Of course, you cannot expand them because this would take exponential time, exponentially many coefficients. But we just plug random numbers into the variables and see whether they match. Just evaluate them, right? So you assume they are given by some method that you can quickly evaluate, like a determinant or something. Okay, so there's a fast probabilistic algorithm for this, and we don't know a deterministic one. And about 20 years ago, Cabanets and Impagliazzo realized something absolutely fundamental, namely that if you find a deterministic polynomial time algorithm for this problem, you would have proved something like P different than NP. It's the analog is in the algebraic method. It's a Valiant theory. You would have proven that the permanent is exponentially harder to compute than the determinant. But anyway, something along these lines. So this, first of all, I want to say is sort of, shocking for anybody who didn't see it before, because an algorithm, a positive result, a fast algorithm implies hardness of a different problem. It implies, a computational hardness result, which is amazing. And I will not go into this. I'm just pointing this out. So I've been, even before this result, this was a basic problem to try to derandomize. So various attempts on many special cases that I worked on and others worked on. There was progress, and of course this result made it far more important. And some years ago, 5 years ago, or 6 years ago, the issue of what happens if these polynomials or rational functions that you are trying to prove are equivalent are not with commuting variables, but are rather with non-commutative variables. Of course, it's natural, and in fact, people worked on related stuff. This became, evident that we needed it in a project here with two postdocs, Pavel Hrubesh and Amir Yildayov, and we started working on this non-commutative version of testing algebraic identities. It's basically the word problem for skew fields. So a very basic problem. And it became apparent from our attempts that invariant theory is absolutely crucial for this problem. I mean, I will not explain it, but understanding the invariance of a certain group action on a set of matrices, understanding the degree of this generating invariance for this invariant ring became essential. And so I kept asking, I started learning about this, and I kept asking people in this area. This was open, and I started collaborating with two students in Princeton, Ankit Garg and Rafael Oliveira. And eventually, cutting a long story short, together with Leonid Gurvitz, we found a polynomial time, deterministic polynomial time algorithm for solving this problem in the non-commutative domain, for non-commutative variables. Nothing like this was known, or even a randomized algorithm was not known, and it used essentially results in invariant theory. And then just trying to understand what we did. I mean, the last 5 years for me was just repeated attempts to better and better understand what we did, the extent of this power of this type of algorithms, what other problems they are related to and or can solve, and what these techniques can do, and what is the meaning of these results. Led, again, being very brief, so I should say first about applications of this. It turns out to capture lots of things that seem unrelated, both work of us with many collaborators, I will maybe not name them all, and understanding that it is useful not just for testing identities, but for testing inequalities, the Braskamp-Libby inequalities. It's good for problems in quantum information theory. It's good for problems in statistics, for problems in operator theory. I mean, it seems to be very, very broad, the very basic questions there. But the more, I would say, fundamental understanding, as we have now, 6 or 7 or 8 papers later, is that what we came about. So, I mean, all these algorithms just evolve along the orbit of a group action on some linear space. That's the nature of all of them. And we have gone to understand that really the appropriate scope of placing these algorithms is as generalization. I mean, many of these these problems are not convex. So standard convex optimization methods don't work for them. And but these algorithms work, and what we understood is that these algorithms are really, or can be viewed as, doing convex optimizations, the standard, first order, second order methods that are used in convex optimizations, only instead of taking place in Euclidean space, they take place in some Riemannian manifold. And the convexity that you need is the geodesic convexity of that space. And by now we have a theory of this kind of algorithms, and of course there's plenty we don't understand, and many of the potential applications that we don't have as efficient. But I think it's I find it fascinating, in particular the growing number of application areas of this. It's really fascinating, and there's lots more to do. And of course, I'm hoping that maybe eventually it will help us solve the commutative case, and understanding what works and what doesn't work there is also fascinating.
I guess this is yet another instance why the two of you are such heroes in the mathematical and computational science community, which brings me sort of artificially, but still, it turns out that it seems that young Koreans have discovered that you're sort of superheroes as well. Your two sons have a common PhD advisor at Stanford, Jacob Fox, as far as I understand, and which was seized upon by a Korean popular science journal for a younger audience, where you and your sons are various characters from Star Wars. As high-profile scientists, do you feel at home at being action heroes in such a Korean thing, with lightsabers and whatnot?
I always like a good joke, so I think this was great, that cartoon.
Yeah, I also loved it, and I think that it just shows that you can be always more creative in getting young audiences excited about mathematics in ways that you didn't expect before.
Before we come to the final ending, there's just one question I'd like to ask that has nothing to do as such with mathematics, and that is, so what is your feeling? Do you feel that science is under pressure? And is this something the mathematical can or should engage in? Well, you have different perspective from where you are. I don't know who of you would like to start that.
Asi has much more experience.
I think that's true. Science is under pressure. And the basic reason for that, as far as I see, is that it has grown very fast, and people understand less and less of what's going on in each particular science, and that makes it frightening, that makes it alien, and also that makes it more difficult to identify what to believe and what not, to distinguish between science and pseudoscience. And this is a real problem. I think we have to very carefully rethink how we teach students in high school. Now, mathematics is one of the areas where the teaching of mathematics is really not up to what it could be. So as long as 90% of the people I meet say, I have always hated mathematics, I think we are not doing our job really well. I'm saying this in spite of some of my best friends are working on trying to improve mathematics education. So in itself, many people realize that there is this problem, but it's very difficult to move ahead. I have less experience with other areas, but I can sort of just looking from the outside to see how biology is different from what I studied as biology in high school, it's clear that there is a huge task there in front of the scientific community. And mathematics should play a central role because it has a lot of sciences are using more and more mathematics, not only statistics, which is sort of standard, but for example, network theory or of course analysis and differential equations and quantum physics, which is really also mathematics, a complicated area of multilinear algebra, so to say. So I think the problem is there, and we should do something about it.
So we would dearly like to ask you what of all you have done you're most proud of, but there's so immense amount, obviously, so it would probably be like asking which of your children you love the most. So on behalf of the Norwegian Mathematical Society and the European Mathematical Society and the two of us, we would like to thank you for this very interesting interview. And again, congratulations with being awarded the Abel Prize.
Thank you. Thank you very much.